In this video, I'm going to discuss a couple of ways to prepare carboxylic acids. So the first way is going to be through hydrolysis of a nitrile. So hydrolysis of nitrile. Now there's an acid catalyzed mechanism for this, and then a base catalyzed mechanism. So I'll first do the acid catalyzed. So I have my nitrile. I'll react this with hydronium ion from the strong acid that I put in the solution that protonates water to hydronium. So now I have the protonated nitrile with a nitrogen that has a positive formal charge. Next, I can have my nucleophilic attack now. Since we're in acidic conditions, my nucleophile will be water. It will come in and attack the carbon, and one of the carbon-nitrogen bonds moves as a lone pair to the nitrogen. So now I have this as my product of that reaction. I need to deprotonate that oxygen to get it down to just OH. So to do that, I'll use water. Again, never any hydroxide when I'm in an acidic solution. So there we go. Now I've deprotonated, so I have a neutral formal charge overall on this compound. So now I'm going to protonate the nitrogen because I'm going to need, ultimately, to get a carbonyl. So I have to get the double bond between the carbon and the oxygen. Right now it's between the carbon and the nitrogen. So I'll protonate the nitrogen. So now that I have that protonated, this will allow me to draw a resonance structure where the double bond now goes between the carbon and the oxygen. So I'll get NH2 down here, and then my R group. So final step, as you can see, is just going to be now to deprotonate. So use water for that. And I'm left with, sorry, I'll draw it a little bit away from the arrow so that way I have room to draw it. I'm left with an amide. So there's going to be another reaction that I'll show you after the base catalyzed mechanism where we go from the amide into the carboxylic acid. So what the hydrolysis of the nitrile does is it gets you to the amide, and then from the amide you get to the carboxylic acid. All right, now the base catalyzed mechanism. It's a little bit simpler because our nucleophile is now a strong nucleophile since it's a base. So there's no protonation step in the beginning. I immediately react with OH minus to get now that. So the nitrogen doesn't have a hydrogen on it, it has a negative formal charge. So this time I need to protonate it. So I'll protonate with water, since now we're in basic conditions, we have no acid. And I know you usually don't draw, in organic structures, don't draw the carbon as a C, but I find it the easiest thing to do because of all these different steps with protonations, deprotonations, nucleophilic attacks. I find it easiest to do. So next step, I need to deprotonate the OH group. So hydroxide again, come in, deprotonate. And now this is in resonance with this structure. So then all I have to do now is protonate the nitrogen. And I get my amide. So a simpler mechanism that has less steps when you do it in basic conditions. So that's an advantage of it, but then the advantage of the acidic conditions is you don't have to use any strong base. Okay, so now that I've gotten the amides formed, I need to hydrolyze the amide to get it to be a carboxylic acid. Like with the first step, you can do this in acidic conditions or in basic conditions. So in acidic conditions first. I'm going to protonate the oxygen. Attack the hydronium, protonate. There we go. Next step is going to be the nucleophilic attack. I've made this, the carbonyl carbon, more electrophilic by protonating the oxygen. So now the lone pair comes in. So now I'll get rid of any of the pi bonds. So now we got a quaternary center. Okay, next step, I need to deprotonate the water that's on the compound right now. So I'll use water to do that. So at this point, I have a diol, right? Two alcohols. I need to get rid of the NH2 group. So the best way to do that is to protonate the NH2. I can protonate with hydronium. So you might be seeing where this is going now. I've made a great leaving group. So I can bump down one of the lone pairs from oxygen and kick off the NH3. So my last step now is simply to deprotonate the oxygen, and this could be done with the water, but it could very likely be done with the NH3 group that just got kicked off too. So either of those would be correct for the mechanism. And there's your carboxylic acid. So that's the acid catalyzed mechanism for going from an amide to a carboxylic acid. Now the base catalyzed, much simpler, just like it was going from the nitrile to the amide. I can get a nucleophilic attack right away, since I have a strong nucleophile. And since I'm in basic conditions, NH2 can act as a leaving group. I don't need to protonate it first. So a lone pair from the oxygen can kick down immediately, kick off the NH2. And that gives me the OH, and then the NH2 will come and deprotonate the hydrogen. So really I get a carboxylate here, but all I need to do is add in, like an acid or something, and then I'll get my carboxylic acid rather than the carboxylate. So the final mechanism I'm going to go over here is a very simple one to go from carbon dioxide into a nitrile. So this would be the reaction of Grignard with CO2. If you're wondering why I'm putting number 3 here, it's because the number 2 reaction was going from the amide to the carboxylic acid. So I didn't label it as number 2, but that was the second reaction. So here, I've got my carbon dioxide, which is a great electrophile because I have 2 oxygens pulling electron density from both sides. So it might be nonpolar because they're canceling out, but it's still a great electrophile. So I'll react with my Grignard. In this case, I'm going to do ethyl magnesium bromide. So basically, I have that carbanion. Or sorry, that's too many. There we go. I have that carbanion. Always number your carbons, right? So this will react. That'll move up, so I'll get that. If this is carbon 1 and 2, this is carbon 2 and 1. Right, that's carbon 3, there's carbon 3. So all of ours are accounted for. Then last step, I just need to protonate. So I add an acid. To protonate, and boom, I've got my carboxylic acid. So that's actually a great way to form them. Only 2 steps. The difficulty is forming the Grignard. They're not the easiest reactants to make because of how reactive they are. But in terms of a simple mechanism, this is a great reaction. Alright, so in the next video, I'm going to start going over how to prepare and then react different of the carboxylic acid derivatives that I went over in the first video.